or a quarter. So this integral here, we could do u sub, we could do trig sub. Which one did you say you wanted to do? Trig sub? Question mark? All right, we'll try trig substitution. All right, so what are we going to let x equal? Let x equal what? It's all based off the radical. 7 sine theta, exactly. 7 sine theta, because I have number minus variable squared. Take the square root of that number, it's 7 times sine theta. So then dx is going to equal 7 cosine of theta d theta. Okay, that's cool. Substitute all that into the integral. See what we get. So integral becomes integral of 7 cubed sine cubed theta square root of 49 minus 49 sine squared theta. And then dx becomes 7 cosine theta d theta. So this is going to be 7 to the 4th power sine cubed theta square root of 49 cosine squared theta cosine theta d theta. 49 cosine squared under the radical, that becomes 7 cosine. So this is going to be 7 to the 5th power integral sine cubed theta, forgot my theta, and then cosine squared theta d theta. So our trig sub integral just turned into a trigonometric integral where we have to utilize our strategy. And here, sine is to the odd power. So I take one of the sines and put it over by the d theta. So this is going to be 7 to the 5th power integral of sine squared theta cosine squared theta sine theta d theta. What are we doing? We're setting ourselves up for a u substitution for cosine. So take sine squared, convert it to 1 minus cosine squared. So this is going to be 7 to the 5th power integral of 1 minus cosine squared theta cosine squared theta sine theta d theta. And now I'm going to let w equal cosine of theta. And dw equal negative sine theta d theta is the derivative. All right, so this is going to be 7 to the 5th power integral of 1 minus w squared negative dw, which is 7 to the 5th power integral of w to the 4th minus w squared dw. So I use that negative sign to flip that parenthesis, make it w squared minus 1, distribute the w squared. So this becomes 7 to the 5th power, 7 to the 5th power times w to the 5th over 5 minus w cubed over 3 plus c. So this is going to be 7 to the 5th power times cosine to the 5th power theta over 5 minus cosine cubed theta over 3 plus c. Now I don't really care about cosine theta. I want to get all the way back to x. So I want to go all the way back to x, which means I need to take this relationship right here, x over 7 equals sine theta, and draw a triangle to satisfy that relationship. So if this is theta, opposite is x, hypotenuse is 7. The adjacent now must be square root of 49 minus x squared. So cosine of theta is adjacent square root of 49 minus x squared over 7. So basically substitute that in for cosine of theta. So this is going to be 7 to the 5th power, 1 over 5 times square root of 49 minus x squared over 7, quantity to the 5th power, minus 1/3, same thing, radical 49 minus x squared over 7 to the 3rd power plus c. That's our answer. Well, of course, pending any mistakes that I made. We don't make mistakes though, do we? That's right, we don't make mistakes. We never, I'm just kidding. You should always check your work. Everybody makes mistakes all the time. Always check your work.
So will that be simplified and make that?
Yeah, I mean, that's good. I wouldn't worry about anything else. I wouldn't try to simplify that any further. Like, I don't care if you write 7 to the 5th is 7 to the 5th or whatever that number is, 49 times 49 times 7. I don't know. Whatever. I don't care. I actually would prefer it if you wrote it 7 to the 5th. So that's just me. All right, so one integral down, 19 to go. It's January 20th. Here we go. 19 more integrals. Let's see what we can do. I'm going to pick some odd numbers out of here. Last quarter, I did a lot of the even number integrals. Now I'm going to see how many odd number integrals I can do. All right, so the first one here in the book we got, it's just one of these problems in 7.5. Integral cosine x over 1 minus sine x dx. So today is all about basically just seeing an integral and trying to figure out how to integrate it. Sounds kind of complicated. Sounds hard. Sounds frustratingly hard. I don't know how to do it. How do I do it? I don't know. I've got to have a strategy. That's the goal for today, is for us to develop a strategy for integration. So I look at this integral and I say, this has got some trig functions in it, but could I do a u sub? That's kind of my starting strategy. Can I do a substitution? So I'll try a substitution. Let w equal what? Yeah, 1 minus sine x. And then dw equals negative cosine x dx. So right away, we can do a substitution and turn this integral into 1 over w negative dw. So it's going to be negative natural log absolute value of w. So it's just going to be negative natural log absolute value 1 minus sine x plus c. Don't forget the plus c. Just like that. Bam. 18 to go. Let me label them so don't forget how many we've done. So we've done 2 integrals now. 18 more. So that's kind of my first part of my strategy. Can I do a substitution? Can I do a substitution? If not, maybe I can do integration by parts. If not, maybe I can use my trig strategies. This kind of is the trig strategy. Can I do a u sub for sine or cosine? Well, here I could do a u sub for the denominator, which included the sine. All right, number 3. The next odd problem in the book is the integral from 1 to 4, square root of y, natural log y, dy. All right, so can I do a u substitution? It's going to be hard because I don't see a 1 over radical and I don't see a 1 over y. So I maybe could, but it might just make me, it might take longer to get to integration by parts. So I think if I did a substitution, I would still end up doing integration by parts. So why don't I just go ahead and do integration by parts? So the solution, try integration by parts. And so I'm going to let u equal what and dv equal what? Out of these two, I have square root of y and I have natural log of y. Which one should be my u? Which one should I differentiate? Yeah, natural log, right? Should definitely differentiate natural log y. And dv is square root of y dy. So then du is going to be 1 over y dy. V is going to be 2/3 y to the 3/2. So this integral is going to become 2/3 y to the 3/2 natural log y minus 2/3 integral 1 over y times y to the 3/2. And this is from 1 to 4. So I'm going to plug in my bounds to the first part, and I'm going to simplify the second part that's still in the integral. So the first part, plug in the bounds, you get 2/3, and then 4 to the 3/2 natural log 4 minus natural log 1 minus 2/3 integral from 1 to 4. Y to the 3/2 minus 1 basically is y to the 1/2. So it's just square root of y dy. So this is going to be 2/3 times 4 to the 3/2 is 8. So 8 natural log of 4. And natural log of 1 is 0, exactly. So this is going to go away. Minus 2/3 times antiderivative of y, or square root of y, is 2/3 y to the 3/2 from 1 to 4. So this is going to be 16 over 3, natural log of 4, minus 4 over 9 times 8 minus 1. So we could simplify that, I guess, as 16 over 3, natural log of 4, minus, see, that's going to be 7, so that's going to be 28 over 9. I feel pretty confident in that answer. No, this is a definite integral. So here we don't have any constants. Only for indefinite integrals we put the plus c in there still. Yes, exactly. Yes, we plug the bounds in after we've applied the integration by parts formula. Yep. All right, that's 3 integrals down. Number 4, have the integral of natural log y over y dy. All right, so we look at this and we say, okay, our strategy is try a substitution. If that doesn't work, try integration by parts. If that doesn't work, maybe it has trig functions. I can use my trig strategy. If that doesn't work, maybe it's got a radical. I can use maybe a substitution or trig sub. If that doesn't work, maybe it's a rational function. I can't use substitution. Maybe I try partial fraction decomposition. So that's kind of our overall strategy. After that, you just got to try to be clever. Hopefully we'll get to some integrals where we have to be clever. So far, it's been pretty straightforward. What do you think we should do here? So let w equal natural log of y, exactly. And then dw, it's going to be 1 over y dy. Exactly. Because I see that 1 over y there, that makes this a very doable integral. So our integral is going to become Integral of natural log of w dw. How do I integrate natural log w? Unless somebody just remembers the antiderivative. Anybody just remember the antiderivative of natural log? Yes, but here we say w ln w minus w. Exactly. So how do we get that? We used integration by parts. So this is going to be w natural log of w minus w plus c. And now substitute what w is. Well, this is going to be natural log of y, natural log of y minus natural log of y plus c. Yeah, doesn't hurt to just memorize that one. Antiderivative of natural log x is x ln x minus x. In this case, we had w, so we said w ln w minus w. How do we get that? We use integration by parts. U equals natural log dv equals dw. That's why I use w instead of u, because sometimes you might have to do an integration by parts after you make a substitution. I like to use w to stay away from using u over and over. It's like, this is my u sub, but now I got to use u for my integration by parts. You can obviously use whatever letters you want for that, but yeah, need letters past u and w. Just u. All right, so we're good. Number 5. It's going to be the next one we have here, integral of x over x to the 4 plus 9 dx. What do you think? We actually did one like this when we covered substitution. So you've actually seen one just like this before. Yes. So let w equal x squared. Then dw will be 2x dx. Well, we have x dx, but we don't have 2, so we're going to say 1/2 dw equals x dx. So our integral becomes integral of 1 over w squared plus 9, and then 1/2 dw. So this is going to be 1/2 integral 1 over w squared plus 9 dw. Now, this is an arctan integral. And we actually, when we were talking about partial fraction decomposition and those types of integrals, this was one of the fundamental integrals. In this case, 9 is actually 3 squared. So this is going to be 1/2 times 1 over 3 arctan w over 3 plus c. So simplify that. It's going to be 1 over 6 arctangent of x squared over 3 plus c. If you forgot that formula, how would you get it? You would factor 9 out of the denominator, make that w squared over 9 plus 1, and then do a substitution for w over 9. Or sorry, w over 3. But in my opinion, it's just, this is fundamental enough just to remember that the integral of 1 over x squared plus b squared dx is equal to 1 over b arctangent x over b plus c. That was the fundamental the fundamental integral from our partial fractions section. All right, 5 down, 15 to go. Number 6, example. Next one is integral from 2 to 4, x plus 2 over x squared plus 3x minus 4 dx. Most of these integrals are kind of a dead giveaway. This one is a rational function. I could try a substitution, but I don't think it's going to work out so well here. But since it's a rational function, I immediately think maybe I should use partial fraction decomposition. So that's what I'm going to go straight for, is partial fraction decomposition. So factor that denominator, hopefully into nice linear factors. So you get x plus 4 minus 1. So that'll give me plus 3 in the middle and negative 4 at the end. So here, I'm going to say that x plus 2 over x squared plus 3x minus 4 equals a over x minus 1 plus b over x plus 4. So I'm going to clear that denominator. So x plus 2 equals a times x plus 4 plus b times x minus 1. So here, since we have linear factors, the best thing to do is use that strategic values approach. Okay, if you plug in very specific values of x, you can get rid of the other constant that you don't know. So here I'm going to pick x equals negative 4. So if x equals negative 4, I would get negative 4 plus 2 equals 0 plus b times negative 4 minus 1. So that's going to be negative 2 equals negative 5b. So b is going to be 2 over 5. And if x equals 1, we're going to have 1 plus 2 equals a times 1 plus 4 plus 0. So that's going to give me 3 equals 5a. So a equals 3 over 5. So this is going to be the integral of 3 over 5, 1 over x minus 1, plus 2 over 5, 1 over x plus 4 dx from 2 to 4. So this is going to be 3 over 5, natural log absolute value, x minus 1, plus 2 over 5, natural log absolute value, x plus 4, from 2 to 4. To plug in those bounds, we get 3/5 natural log of 3 plus 2/5 natural log of 8 minus 3/5 natural log of 1 minus 2/5 natural log of 6. And I don't know, probably the only thing I really want to simplify here, this natural log of 1 is going to be 0. And I could combine these two since they have the same coefficient. I could say this is going to be 3/5 natural log of 3 plus 2/5 natural log of 8 over 6. Which of course could reduce to 4/3. So you could call it 3/5 natural log of 3 plus 2/5 natural log of 4/3. So I probably won't simplify it any more than that, although we could pull those coefficients in as exponents and then combine it. That's just kind of unnecessary. This is pretty good. All right, so that was number 6. All right, the next one is very similar to the problem you asked at the beginning of class. It's 1 over x cubed square root of x squared minus 1 dx. So basically just took the numerator and put it in the denominator. I think the one we started with was 49 minus x squared. Well, here we have x squared minus 1. So it is going to be a secant versus a sine, but it's similar. So what substitution are we going to make? I just gave it away. Shoot. X equals secant theta. Dx equals secant theta tangent theta d theta. So our integral will be the integral of 1 over secant cubed theta square root of secant squared theta minus 1. And then dx is secant theta tangent theta d theta. This will be the integral of 1 over secant squared theta square root of tangent squared theta tangent theta d theta. So basically I'm canceling a secant here, making that square. And square root of tangent is tangent, that cancels with tangent. 1 over secant is cosine, so this is the integral of cosine squared theta d theta. What do we do with cosine squared? Power reduction is exactly right. So this is going to be integral 1/2 1 plus cosine of 2 theta d theta. So that integral is going to be 1/2 theta plus 1/2 sine of 2 theta plus c. Now, I'm going to go ahead and simplify this a little bit. I'm going to write 1/2 times theta plus 1/4 times 2 sine theta cosine theta plus c. I prefer to write it that way because I'm going to have to substitute everything back in terms of x, and I want to get sine 2 theta in terms of just sine theta cosine theta, which I can get from my triangle. So our triangle here says that secant theta equals x, secant theta equals x. So draw a triangle to satisfy that. So hypotenuse is x, adjacent is 1. Other leg is x squared minus 1, take to the square root. So I guess we could say theta is the arc secant of x. I don't like that too much. I'm going to say x is, or theta is the arc cosine of 1 over x. I'm going to write it like that. I like that better, personally. Neither one's wrong, but I'm going to write it that way. So this is going to be 1/2 times the arc cosine of 1 over x plus 1/2. And sine theta is the opposite, which is the radical, x squared minus 1 over the hypotenuse x. Cosine theta is going to be 1 over x plus c. And that's good enough for me. No, I had some freedom there when I needed to substitute in for theta. I chose to substitute theta as arc cosine of 1 over x. I could have done arc sine of radical over x, or I could have done arc tangent of radical. It just, whoops. Just depends on what you want to do. These are the problems in 7.5. 9, 11, 13, 15, 17, and that was number 19, actually. So cool, cool. 7 integrals. We are not going to make it, are we? 1143. I guess I could just work and not tell you anything. That would be dumb. That would be dumb. What's up? Oh, yeah. A lot of writing. Yeah. All good? It's all good. What's up? We can try to do half of 20. We should definitely get to 10. This is number 8. All good. All right, let's keep going here. Next one is the integral of cosine cubed x over cosecant x dx. Okay, what's up? Yeah, so I'd like it to all be in terms of sine and cosine, preferably, since I have cosine in the numerator already. So just kind of trial and errors is kind of the strategy here. Since it's trig integrals, I'm trying to use the substitution method, but I need a cosecant to turn into a sine first. So this is going to be cosine cubed x times sine x dx. So that was the only thing we had to do. Now what can we do? Actually, I'm just going to go ahead and let w equal cosine. So let w equal cosine x, and then dw be negative sine x dx. So this is going to be the integral of w cubed negative dw. So that'll be negative 1 over 4, w to the 4th power plus c, which is going to be negative 1 over 4 cosine to the 4th power x plus c. What we got? Cosecant is 1 over sine, so 1 over cosecant is sine. All right, so cosecant is 1 over sine. So sine is 1 over cosecant. All right, cool. That's 8 integrals for the day. Do number 9. Example. Oh, I like this one. Integral of x secant x tangent x dx. So it was okay if we just had secant times tangent. Antiderivative of secant times tangent is just secant. Bam, that's easy. But there's an extra x in front of that. Yes. Yeah, do integration by parts. So what are we going to do? U equals x and then dv secant times tangent. Because I can integrate, or I can anti-differentiate secant times tangent. So if that's my dv, I can get v no problem. So v equals secant. Du equals dx. Solution. This is going to be x secant x minus integral of secant x dx. So uv minus integral v du. And here we are again, antiderivative of secant. Natural log secant plus tangent, exactly. And like I said, remembering the trick is just as difficult as remembering the antiderivative directly, so might as well just remember the antiderivative directly. So yeah, this is going to be x secant of x minus natural log absolute value secant x plus tangent x plus c. Just like that. That's a good integral. The next one, integral from 0 to pi, t times cosine squared t dt. I've actually never worked any of these integrals before in my whole life. Believe that or not. This is a new edition of the book. And last quarter, I worked some even problems. And so now I've worked the odd problems. I've never worked any of these. What do you think we should do here? What is it? Go ahead and use power reduction. That's a good idea. I was going to do integration by parts first and then use power reduction in the integration by parts, but either way, yeah, let's go ahead and use power reduction. Sure. So the solution here, use power reduction first. So integral from 0 to pi, t times 1/2, 1 plus cosine of 2t dt. So that's going to be 1/2 integral 0 to pi, t plus t cosine 2t dt. So the first integral, or the first term, t, I can integrate that, no problem. The second one, t times cosine of 2t, that's integration by parts. So this is going to be 1/2 times t squared over 2 from 0 to pi plus integral from 0 to pi t cosine 2t dt. So what should we do? We said it already, integration by parts. U equals t dv equals cosine 2t dt, du equals dt, v equals 1/2 sine 2t. All right, so this is going to be 1/2 parentheses pi squared over 2 plus t over 2 sine 2t from 0 to pi minus integral 1/2 sine 2t dt from 0 to pi. This middle integral, or this middle term here, sine of 2t, if you evaluate that at pi, that's sine of 2 pi, that's 0. Sine of 0 is 0. So this actually, in the middle, is going to go to 0 for both of these terms, pi and 0 plugged in. So that middle term goes away, which is nice. So this is going to be 1/2 times pi squared over 2 minus 1/2 times negative 1/2 cosine 2t from 0 to pi. Because the antiderivative of sine 2t would be negative 1/2 cosine 2t. So this is going to be 1/2 times pi squared over 2 plus 1/4 and cosine of 2 pi minus cosine of 0. Well, that's 1 minus 1. So this whole thing goes to 0. So it's just pi squared over 4. So our answer is just pi squared over 4. Is e to the x plus e to the x dx. So the exponent of e is x plus e to the x. So that seems a little weird. So it's e to the x plus e to the x. Makes sense. The whole exponent is x plus e to the x. All right, so what we should do first is actually just some algebra. We're going to break this up and say this is going to be e to the x plus e to the times e to the x dx. So what are we going to do? Go through our strategy. Can I make a substitution? Yeah, let w equal e to the x, and then dw will be e to the x dx. So here is my dw. So this really just becomes integral of e to the w dw, which is e to the w plus c. So this integral is really just e to the x plus c. Just like that. The next one, arctangent square root of x dx. Ooh, seems tricky. Seems tricky. We actually did one like this in class. We did arc sine. No, we just did sine of square root of t or something like that. Well, this is arctangent square root of x. Eek. How do we do it? I guess we could just go straight for like integration by parts. You want to just go straight for integration by parts, or do you want to be clever? Let's just go straight for integration by parts, not try to do anything too crazy. All right, so if we do integration by parts, we're going to let u equal arctangent square root of x, and dv is just going to be dx. And then the derivative here, we have to be pretty careful. It's going to be 1 over 1 plus square root of x squared is just x, times the derivative of square root of x, which is 1 over 2 square roots of x. V is going to be x. So this integral is going to become x arctan square root of x minus 1/2 integral square root of x over 1 plus x dx. Because the x over square root of x would become square root of x in the numerator when I multiply the v du. Oops, that should be du. Sorry, I put the dx on the wrong side. Du equals this dx. Sorry. Okay, so now we're trying to figure out how to do this integral here. square root x over 1 plus x. Maybe we're going to have to go to that clever step anyway. I don't know. I'll just tell you what I'll try to do. I'm not going to try to be super clever. I'm just going to try to do a regular substitution. So let w equal 1 plus x, and then dw will be dx. But x would be w minus 1. So I'm going to substitute all of that in. So this is going to be x arctan square root of x minus 1/2 integral square root of w minus 1 over w dw. Maybe I should have tried something different. Let's try a different substitution. So this is kind of not really getting us anywhere. So let's try a different substitution. So it's a little more clever. Let's try a different substitution. W equals square root of x. So then x equals w squared. So then dx equals 2w dw. So let's try this instead. So this is going to be x, x arctan square root of x minus 1/2 integral w over 1 plus w squared, and then dx is 2w dw. So if we simplify that, that's going to be x arctan square root of x minus integral w squared over 1 plus w squared dw. Okay. Everybody follow so far? So we did make a little bit of a clever substitution. That was the one I wanted to make initially. We ended up having to make it here. So it probably would have saved us a little bit of heartache if we had started off with x equals w squared, basically to get rid of the radical from the arctangent. Now here, I'm going to do one more thing that's maybe a little clever. It's not really, I'm not saying I'm clever when I'm doing it. I'm just saying it's clever because I've seen it done before. Whoever came up with this, it was brilliant. It wasn't me. So don't be fooled. I don't tell you that I've done all these integrals. This is the first time I've seen these integrals because I want you to think I'm awesome, which I know you all do. I want you to know that this is kind of how I approach integrals for the first time when I see them. That's the point of this, okay? That make sense? Cool. So here, I'm going to do a little trick that's very common when you have rational functions like this specific one. If I write 1 plus here and then minus 1 here, I've not really changed anything, have I? It kind of, it doesn't make me do the long. Normally, I would do a long division right here. But if I just add and subtract 1 in the numerator, it allows me to kind of skip a step there. So this is going to be x arctan of square root x minus the integral of 1 plus w squared over 1 plus w squared minus 1 over 1 plus w squared dw. So I just broke that numerator up. Now I have 1 plus w squared over 1 plus w squared. What's that? It's just 1, right? So this is going to be x arctan square root of x minus the integral of 1 minus 1 over 1 plus w squared dw. So that's going to be x arctan square root of x minus w plus arctan w plus c, and w was square root of x. So this is going to be x arctan square root of x minus square root of x plus arctan square root of x plus c. That was a pretty legit integral. It's a little tricky. A little tricky. All right, one more I want to do, and we'll have to call it a day here, I guess. Couldn't make it to 20. Like, only do 13. That's a good number to stop on, I guess. 13. So number 13. Integral from 0 to 1, 1 plus the square root of x to the 8th power. Let's make it a little spicy, though. Let's not do the 8th power. Let's do the 2021 power. So 1 plus square root of x to the 2021 dx. Because there's actually nothing special about the 8th power. So I'm going to use the 2021st power. Because it's 2021. Any ideas? Substitution. All right, so I'm going to do let w equal 1 plus square root of x. And I'm going to solve for x. So w minus 1 would be square root of x. So w minus 1 quantity squared would be x. Now take the derivative of x with respect to w on the left. So we get 2 times w minus 1 dw equals dx. So that's a dx that I'm going to substitute. I've got w for the 1 plus radical x, and now I've got to change the bounds. Might as well. So if x equals 0, w equals 1, and if x equals 1, w equals 2. So I'm just going to go ahead and change the whole integral. So that's going to be the integral from 1 to 2, w to the 2021 power times 2w minus 1 dw. Not as bad as we thought it was going to be. She made a good substitution. So this is going to be 2 times the integral from 1 to 2, w to the 2022 minus w to the 2021 dw. I can integrate powers, no problem, even if they do look silly. These aren't silly, these are legit. This integral got more legit when I changed that power. That's right. So this is going to be 2 times 1 over 2023, w to the 2023, minus 1 over 2022, w to the 2022, from 1 to 2. So I guess that's a bad thing. I'm doing 2 to the 2023 power. That's probably kind of big. So I'm just going to leave it as 2 to the 2023 and 2 to the 2022. And 1, I got that, no problem. I can do that. 1 to the 2023, that's no problem. I got that. So this is going to be 2 times 1 over 2023, 2 to the 2023, minus 1 over 2022, 2 to the 2022, minus 1 over 2023, minus 1, or plus now, 1 over 2022. And I'll just leave it like that, I guess. Probably is a lot cleaner when you use the 8th power. You can actually raise that 2 to the 9th power, 10th power, whatever you have to do. which is 1,024. That's not too bad. I wonder if anything could even compute 2 to the 2023. I doubt it. I doubt anything online could even do that. 2 to the 2023. That'd be interesting. Okay, well, we made it to 13. We're lacking 7. Sorry about that. Hopefully you don't feel shortchanged. People are always asking for more examples, so I gave you 13 today. Trying to get them out there. Trying to get them out there. Calculator says error. Okay, 1 second. Don't go anywhere.